with locus, which was variation, part of root location, as gain is varied. Gain is varied. Is varied. Now, this week we are going to discuss about frequency response methods. What happens with frequency response methods is that if you have your system G of S, you give it a sinusoidal input x of t, no, x of s. Let me just x of t is equal to sine omega t plus some angle, or just call it sine omega t, assuming the phase angle is equal to 0, which you can also get it x of s is equal to, from the tables. What is interesting in having this system is that the output is also 1 sinusoidal, 2 same frequency, number 3 change in amplitude, and number 4 change in phase. That is it is a system, G of t or G of s. If this is x sine omega t, then this becomes, the output becomes y of t is equal to x sine omega t. There is a phase change and there is some amplitude change. The input and output are the same. Say that if this was your input signal, then the output is also a sinusoidal. Let me use a lower amplitude. It could be. So there's some phase difference here, and there's a change in amplitude. But if I was to plot on the same axis, I could do this way. So there are 4 things that happens. One, it is sinusoidal at the same frequency. This is actually 1. Sinusoidal at the same frequency, there is a change in amplitude and there is a change in phase. So frequency response methods are methods in which you apply an input which is sinusoidal and the frequency starts from 0 all the way to very high. And then you start the response. Now, as the order of the system increases, as the order of the system increase, use of time domain methods become difficult to analyze. Instead, we use frequency response methods. We apply a sinusoidal input and observe the steady state response. And the frequency is varied from very low to very high. Usually 0 to about infinity. These methods offer the advantage that the mathematical model of the system is not necessary. So what happens is that you can apply some sinusoidal input, and then the output you study on an oscilloscope, cathode ray oscilloscope. So if it's a dual channel, channel 1, and then the output is channel 2. What you can now see is that you can see the signal applied, and then you can see the response, y of t. So you don't need to know the system model. Not necessary to know the system model. I mentioned this that if the input is sinusoidal, the output is also sinusoidal with some amplitude change and phase change. So frequency response methods, we are going to study the amplitude and the phase. And we are going to plot amplitude and phase of G of S. If we plot it a linear plot, we are going to come up with 3 plots. Same info, different presentation. M at an angle theta can also represent as M e power j theta. It's the same representation. Magnitude at an angle theta. Usually you replace S is equal to j omega. So G of S becomes G of j omega, which is complex. Complex means it has got real part plus j imaginary part, which you can get the magnitudes real squared plus imaginary squared is equal to m tan inverse imaginary over real 5. Yes. So we first express G of j omega into real and imaginary parts. Then if you get the magnitude, it's G of j omega. If you get the phase, that. And then you plot. So what you're basically going to do, you are going to plot what's known as sinusoidal transfer function G of j omega is equal to G of j omega magnitude at an angle of G of J omega, which is equal to M at an angle of phi. These are frequency response methods. I explained this that this could be your x of t with some amplitude, and this is y of t. So there's a change in amplitude, and there is a phase difference, phi. So this could be an image of an oscilloscope showing the two. That you have M and phi. Now we are going to get 3 drawings. Drawing number 1. If you make frequency against magnitude, and frequency against phase. So for every frequency omega, because frequency ranges from 0 all the way to infinity, we can use semi-log. That is, you start from 1, 10, 100, 1000, 10 power 4, 10 power 5, all the way. This becomes a semi-log coordinate in one axis. You get a Bode plot. So you'll have 2 drawings. Number 2. Usually, magnitude is plotted at 20 log magnitude. So that is Bode plot. Number 2, polar plots. If you use polar coordinates, say that you get at an angle phi, you get phi m. At phi is equal to 0, what is m? At phi is equal to that, what is the m? And then you get drawings like that. These are polar plots. Number 3, if you plot magnitude and phase, this is phase, and this magnitude. You get magnitude versus phase plots. If you replace it with if the magnitude is in dB, 20 log magnitude in decibels, then you can come up with what is known as Nichols chart. I gave you 2 reference books. This is Shom. We have Nyquist methods. We have done root locus, it's time domain. We have Bode plots. And we have Nichols chart. Nichols chart is magnitude versus phase plots. Magnitude is phase versus magnitude, which you can plot on just a linear chart. I'm just going to mention this. And I think my mentioning of Nichols chart, I would want you to read this on your own. Nichols chart. I will also not mention, or I will not want to talk about Bode plots. Bode plots. Oh, Bode plots are still down, eh? Bode analysis, yes, Bode plots. I want you to read because I've given the notes for Bode analysis or Bode plots. Even in this other book, you still have the same. So I will leave it at that. I will only discuss Nichols, Alonso Nyquist, or polar plots. But basically the same information. The approach is to draw a table. Frequency G of J omega and the angle. Frequency 0, 10, all the way to 10, or call it all the way to infinity. You have values. So you have omega, you have G, and you have magnitude, and you have the angle. So from this data, you can develop 3 different drawings. One is G versus omega, and angle G versus omega. But this 20 log. Come up with Bode plots. Polar plot, you come up with Nyquist plot or polar plot. Linear plot, you come up with Nichols. All these plots represent the same information. Now, from these plots, you can, from the 3 plots, you can come up with different specifications. An example, this is a Bode plot. Where you have gain versus frequency, and you have phase versus frequency. So there are usually 2 plots. These are 2 Bode plots. From this Bode plot, you can see we have a peak. From the peak, we have a point in which the value goes below 1 over root 2, which is equal to 0.707. Anything above this 1 over root 2, you define it as a bandwidth of operation. Bandwidth. At the peak, this corresponds to the resonant frequency. This information can also be found from the other plots. So, but we're just going to define this based on the Bode plot. Resonance frequency. This is the frequency at which the resonance peak occurs. Or we have a resonance peak at which the closed loop frequency response attains its maximum. Peak resonance, and this occurs at peak resonant peak, and it occurs at resonant frequency omega r. Bandwidth is the range below which the magnitude falls 1 over root 2 is equal to 0.707. In dB, 1 over root 2 in dB, 20 log. One over root 2 is equal to negative 3 dB. So negative 3 dB, 0.707.1 over root 2 half power points when this was, if this was voltage, is 1 over root 2. So if to get power is voltage squared over R. R normalized to unity, so it becomes half. So power is half, so it's called half power point. Cutoff rate is the slope of the curve near the cutoff frequency. So you see this slope. Some systems may have very high cutoff rates. There are those ones which may have very low cutoff rate. So these are some of the definitions. Now, you have notes for Bode plots. I will not want to talk about it, as I said, but I've just said you have two drawings similar to this. One is a phase, the other is a magnitude, and the x-axis is logarithmic. Log. And this G of J omega etc. So we leave Bode plots, Bode diagrams. In all this, we are going to have this kind of table. We get G of S. We replace G of J omega. Get the magnitude. So depending, the magnitude can be either be logarithm or just not logarithm. So for body, it is body plot is logarithm, magnitude and the angle. I will not go to that. But this is a Bode plot of 1 over. Or as an example, you see 1 over S plus 1 is 1 over s plus 1 a. So replace s is equal to j omega. It becomes 1 over j omega plus a. So if a is equal to 1, it becomes 1 over j omega plus 1. And then you get magnitude. Magnitude of this is 1 over in dB it is easier because when you divide it's minus 20 logarithm. But in actual sense, if you are to get the magnitude, then I will separate this into real and imaginary parts. Imaginary parts by rationalizing. This may not be a very good example, so let's just leave that. Okay. Polar plots. Now, we are going to discuss plots. In polar plots, we plot the magnitude and the phase. As an example, 1 over s plus 1. What is the magnitude? So, this is G of s. G of j omega. G of j omega is 1 over j omega plus 1. G of j omega, magnitude. So I multiply this by the conjugate. This becomes minus j omega plus 1 minus j omega plus 1. This is rationalizing the denominator. Rationalize, denominator. That is 1 over a plus root 2. You recall root b. We multiply by a minus root b. A minus root b. This becomes a minus root b over a squared plus b squared. Now, if you do this, you get 1 minus j omega over omega squared plus 1. Real part, 1 over omega squared plus 1. Imaginary part, minus omega over omega squared plus 1. Getting magnitude. Getting magnitude is 1 imaginary squared plus omega squared under root over this common LCM, magnitude, real part plus imaginary part. under root. So this 1 squared plus minus 1 squared minus omega squared, which is over, the denominator is 1 plus omega squared, which is equal to 1 plus omega squared under root over 1 plus omega squared. So this square root will cancel, becomes 1 over omega squared under root, which is given by this. Angle phi is equal to tan inverse imaginary over real. So minus omega over omega squared plus 1 divide this imaginary over real over 1 over omega squared plus 1. The denominator cancels, becomes minus tan inverse omega negative, which is equal to negative tan plus omega. Now, this I've just picked random. Numbers here. With practice, it will show you that you need to concentrate on the numbers around 0. So 1 over omega squared under root. If omega is equal to 0, this becomes 1 plus 0, which is a 1. Tan inverse omega. Negative tan inverse 0 is a 0. Let's put omega is equal to 1.5. 1 over 1 plus 0.5 squared under root is equal to 1 over 1.25, which is equal to 0.89. Can somebody confirm? You need calculators. You need calculators to do this. Can somebody confirm the tan inverse 0.5? I can do that. Calculator. 0.5. Shift second function. Second tan. 26 degrees. 26.56 is 27 degrees. If omega is equal to 1, tan inverse of 1 is 45 degrees. That one we all know. And 1 plus 1 squared, 1 over 2. 1 over 2 is 0.707. Tan inverse of 2. 2 second. Tan inverse of 2. And 1 over 1 plus omega is 2 squared under root is equal to 1 over 5. 1 over root 5. 1 over root 5. So I'll get 1 over root 5. 5 root of 5 is that reciprocal. 1 over. Oh no, it's this 0.44. Yeah, 0.447, 0.45. Let's go to omega is equal to 5. 1 over 1 plus omega squared is 1 plus 25. And tan inverse 5. 26 under root. And then reciprocal, 0.19. And is that. And the angle tan inverse 5. 5 trigonometric second tan inverse 78 degrees. 78 degrees. And so on. When you get to infinity, 1 over infinity is equal to 0. Tan inverse infinity is usually 90 degrees. This is how you populate this table to get polar plot. It's a similar table to that of Bode plot. Now, how do I plot now? Magnitude and angle. At an angle 0, this is a polar plot. And the angles are counted counterclockwise. So a polar plot something like that. The graph of a polar plot. The magnitudes go radially outwards and the angles. So this is positive angles. Positive angles. This is negative angles. Negative angles. Now, we need now to plot this. When omega is equal to 0, what is the magnitude? The magnitude is 1 at an angle of 0. So, 0 degrees is that line. And the magnitude is 1. 1 at 0 degrees. Let's come the next. Negative 27 degrees. The angle is 0.89. So I'll come here with a protractor. I'll measure negative 27 degrees. And I measure with a ruler 0.89. .45 degrees is here. It's around 9. Is 45 degrees is somewhere there. Negative. The angle is 0.707. The length is 0.707. So this distance is 0.707. Come to negative 78 degrees. 78 degrees is close somewhere here. That is 28 degrees. The distance is 0.19. 0.19. Come to negative. The distance 1. That's around 0.84 is around there. The distance could be 0.1. Or 0.1 is around here. I'm just doing approximation. And finally, at infinity, the angle is 90. This angle is negative 90. This, if you measure from that, is negative 90. And the distance is 0. So I'll join these parts. I'll go that direction. That direction. I join the dots. I join these points. And I get the polar plot. Polar plot. So check, we have taken this. Look at the second example.
Mr. When
Yes.
you are quoting, you start from anywhere or you have specific point?
You start from omega is equal to 0 to infinity. Put some 3 or between 0 and 1, put some 3 values. 0, 0.1 or 0.1. So omega is between 0 and infinity. This will give you, so you can start at any within, because these points are unique. But as long as you have 0 to infinity and you have more concentration around this point, when you come to 5, you will jump probably to 100. You can jump to 1,000 or 10,000. So you can have about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have very good calculators which you can feed this formula and you'll just be keying in the value of omega. So you can program a calculator, give you the value of omega, you get this very fast. And angle. So you can start anywhere as long as omega starts from. So at this point, you know omega is equal to 0. Omega is equal to 0.5 all the way. But you are not interested in omega. We're only interested in the plot of omega of the phase versus g magnitude in polar coordinates. Polar coordinates. Now, the second example. Oh, this is not worked. 10 over j omega. J omega plus 1 is equal to 10 over j omega minus omega squared. You have very nice calculators. You have calculators which can do complex numbers. So you can just put your formula. Actually, there is a function called rectangular to polar. What's rectangular to polar? I want you to work out. I mean, the calculator that I know how to use is a very old one. I know this one of doing only addition and subtraction, step by step. So this one, you can rationalize. Let's just do together this. We are going the long step, but we are going the long step. But if you had, or rather if I had a calculator, I could have learned how to use it. Does somebody among us know how to just get the magnitude and phase? You're going to learn. Okay, let's go the long method. Is equal to, so rationalize first. 10 over plus j omega. And then I multiply by omega squared minus j omega. Minus omega squared minus j omega is equal to negative 10 omega squared minus 10 j omega over omega power 4 plus omega squared. this squared plus this squared. So real part minus 10 omega squared over imaginary part is equal to minus j 10 omega over magnitude. I can factor out 10, 10 omega squared power 4 plus omega squared under root over this is the same LCM, which basically is equal to 10 over square root of and the angle tan inverse imaginary over real. So imaginary is omega over omega squared. Omega over omega squared negative. So it's equal to omega over omega squared is equal to negative 1 over omega. Now you have your table now. Omega. You have G of J omega magnitude and the angle G. Let me do the correct thing. G of J omega magnitude and then angle of G of J omega. And then we say we get around 10 points. I say we start with 0. 0.05, 0.2, 1, 5, 100, 10 power 6, infinity. So at least table 1, 2, 3, 4, 5, 6, 7, 8. Call it 8. 8 to 10. And then with this, you can just program your calculator. Who has a scientific calculator? Can you do, I think it was 10 divided by brackets SQ RT alpha. Is it alpha? You press alpha A squared plus alpha alpha A to the power 4 and then bracket. And then when you press calc, it tells you alpha is equal to omega is alpha is equal to, you put 0, it gives you a value. You press calc again, you put 0.05, it asks you alpha is equal to, you put 0.5. So you get these values very fast. I'm sure you, I don't know, this is a calculator that I used to test this alpha functionality. Does anybody of you has a calculator which you can program just to give us these values now? I don't know. I think I removed my MATLAB. Let me check this scientific calculator if I can. No, this I cannot. So we may not proceed with this because of unless somebody can assist us in getting this. This is how to go about it. Once you get these values now, once you get the values, now you plot. So you can do this. Before that, you can do this 45. You can just get a plain paper. Okay. You can get a plain paper, measure 0, 45, 10, 20, 30, 45, all the way, all round. I will see if I can, it's not a standard graph. Getting it is not easy in the standard graph, but you can generate it from MATLAB. So after you do that, after you get this values, you do your polar plots. And just for demonstrations, let me just go to Nyquist plots in this textbook. Nyquist. Yes. Okay. This is a polar plot. And this is a Nyquist chart. Polar. No, this is board. This is polar. And this is Nichols. And I want to tell you that you can get MR from any plot. MR. All the three plots have the same information. So we're only dealing with this polar plot, which I wanted us to see some of the plots. Yes. You see, like this plot, when you have 1 over G of J omega, G of J omega is equal to 1 over S. Meaning 1 over J omega, the angle is equal to tan inverse real over imaginary. This is equal to J omega over negative omega. I multiply times negative J omega, negative J omega. No. J omega, 1 over J omega, followed by negative J omega, negative J omega. You get negative J omega over omega squared, which is equal to negative J over omega. Tan inverse imaginary over real is equal to tan inverse imaginary is negative, J is negative 1 over real. This number is purely imaginary, negative J over omega is purely imaginary, so over 0. And tan inverse that is equal to negative 90 degrees. And you can see that for whatever value that you get, the angle will be negative 90 degrees. So if you start at omega is equal to j over omega. Omega is equal to infinity. Let's start from to 0. Then you get a 0. When you get omega is equal to 1,000, 1 over 1,000 is 0.001. So word plot. So infinity, it becomes a 0 at an angle negative. When you get 0.001 at an angle negative 90, the angle negative 90 is that, but 0.01. When it is 1 over 0.001 is 1,000. So it's 1,000, which is here, at the angle is negative 90. And therefore you find this in that direction, this one. Can be plotted from 90 degrees, from the center of the circle, that way. 1 over j omega t takes this form. So you can study this plots. You can study these plots. There are so many. We are dealing with this. Oh, this deals with dB. I want those ones who don't deal with dB. That's the mistake. But generally, they take, like, for example, the first order system is this. The second order system is this way. This 1 over 1 plus j omega. 1 over 1 plus j omega t1 1 this j omega t. T is just a constant, 1 plus j omega t2. T1 and T2 is a second order. It takes this form. And so forth. So this you do by observation. There are quite a number. I don't know whether this book provides. Let me see which books is better. Just to observe Nyquist 299. 299 to 22. 299. Yes, these ones. This is like a third order system. This 1, 2, 3. I've told you a second order system will start from here. A first order system will be is first. Second will be something like this. Third will be something like that. See? But now this is only drawn, not complete, it has not crossed. Yeah. This looks like a third order. 1 over j omega, j omega, j omega. Because so you look at all these examples for Nyquist plots, 299. These ones, yes. Now, let's now see stability. Once you plot your polar plot. Do stability analysis. Using the polar plot. You can also use the others. but we only deal with the polar plot for now. Now, we have something known as Nyquist stability criterion, which relates, this is a closed loop. Poles of the closed loop must lie on left hand side of S-plane. However, Nyquist criterion relates poles of open loop GH of S. Recall, this is 1 plus GH of S closed. This is open. GH of S open. So if you plot GH of S, if you plot polar plot of GH of S, we can determine number of poles of 1 plus GH of S. That lie on right hand side of S-plane. Number one, we know how to plot polar plot. Two, to determine stability of a closed loop system, we can consider only GH of S. We can consider only GH of S. Once you consider GH of S, we use Nyquist stability, criterion. Now let's read the notes. For stability, the poles of the Q of S, this Q of S, must lie on the left hand side of the S-plane. This one we all know. And to determine this, we used Howitz criterion. But now, Nyquist allows us only to consider GH of S. Nyquist criterion allows us to consider only GH of S, the open loop. The poles of GH of S, GH of S, poles may lie on right hand side, but system is stable. But 1 plus GH of S must on left hand side. I want two statements. In determining stability, the poles of the equation Q of S, which is equal to 1 plus GH of S, they must all lie on left hand side. But the poles of G of S, GH of S, the open loop, can lie on the right hand side of the S-plane, but once you add 1 plus, they must all lie on the left hand side of the S-plane. Nyquist stability relates the number of poles on the right hand side the poles of G of H of S, which are on the right hand side, to the stability of the system. So you can use the poles of GH of S on the right hand side to determine the stability of the system. Nyquist stability criterion relates the open loop frequency response G of J omega, H of J omega, to the number of poles that lie on the right hand side of the S-plane. We only consider GH to determine the poles of 1 plus GH. Now, I want us now to study this. It says for stability, as omega is varied from negative infinity to infinity, the locus of G H of J omega must encircle the point -1 plus J0 K times, where K is the number of poles of GH of J omega that lie on the right hand side. Let me explain this. Use your polar plot. GH of S. Ideally, I was supposed to plot 1 plus GH. But now, if I don't plot 1 plus GH, it means I've shifted the center. I've just plotted this vector. I've plotted 1 plus 1 GH of S shifted to by 1. So meaning there is a point -1 plus J0. This is 0, 0. This is 0, 0. -1 plus J0. So it says, as I plot the locus of GH of S, of J omega, now I replace S with J omega. J omega. If GH of J omega has a pole on right hand side, then if it is as called one pole on right hand side of the S-plane, then the locus must circle this point once. Then the system is stable. So if we have two poles on the right hand side of g of h omega, then the locus must cycle this point twice. Must counterclockwise twice. It means if gh of j omega has a pole on the right hand side, for 1 plus gh of s to be stable, then we have to circle the point negative 1 plus j0 k times the number of times gh of j omega has poles on the right hand side. Am I coming clear? I guess so. Let me check if we have an examples for this. Okay, there is a very complicated mapping theorem, which you are not dealing with the mapping theorem. You see this point, This locus must encircle these points in that direction. But if there is no pole, if gh of j omega has no pole on right hand side, k is equal to 0, then the locus should not cycle negative 1 plus j0 because k is equal to 0. If we have one pole, it should cycle one time. If we have two poles, it will cycle twice for stability. Otherwise, the system becomes unstable. Let me check a locus which circles more than once. Oh, that one. Yeah. You see like this. How can I put this? This circle counterclockwise. It should be counterclockwise. For this system is stable if only GH has no pole. On right hand side. This negative j0. Another example of circling. For example, let's look at this example. This GH of S. GH of S has a pole on right hand side at S is equal to 1 over T, this one. For stability, locus must encircle point negative 1 plus j0 once counterclockwise. And the locus yes, I've mentioned it has one pole at S is equal to 1 over T. Therefore, it has K is equal to 1. This point circles the point 1 clockwise. it circles clockwise. Meaning, because it is circling clockwise. Once. Then it is unstable. If it was counterclockwise, if it is counterclockwise once, and we have one pole on the right hand side, then we'll say it is stable. Let's look at this example. If you put k is equal to 1 to plot the, you put k is equal to 1 to plot the Nyquist. So we have one pole at s is equal to 1 for GH. So we have to investigate now 1 plus GH. We do this by plotting the Nyquist chart, Nyquist plot. So this is the Nyquist plot of k s plus 3 over s minus 1. So this has got one pole on right hand side. Then when we plot the polar plots, it encircles the points -1 plus j0 once, counterclockwise. You can see the counterclockwise, this arrow, once. Then this system must be stable. K is equal to 1, and then once, it's encircled once, counterclockwise. Then the system must be stable. Let's check what is the verdict of this. Yes, the open loop seems to be unstable. You see, the verdict says the open loop is unstable, but the closed loop is stable. Open loop has got one pole on left hand side, but the locus or the Nyquist plot encircles this point once. Counterclockwise. Then the closed loop become stable. Now, let me look for you an assignment to give you. It's from this book. Okay, I'll give you shortly. Before the end of this, I'll give you an assignment to work out on it to determine the stability of the system. Now, I go back. I've been trying to explain the Nyquist stability criterion. But first, we only consider GH. So we plot the polar plot for GH of S. We plot the polar plot of GH of S and then see the number of poles on the right hand side. The number of poles on the right hand side should equal to the number of counterclockwise encirclement of the point 1 plus j0. So as omega is varied from negative to infinity, the locus of this point the number of times equal to the poles of G of H that lie on the right hand side. Now, once you have your Nyquist plot, there are some factors or definitions which are related to control. Recall, when we had our system K over a polynomial, K was the gain. And we realize that sometimes K has got a value, a maximum. K min to maximum. The value of gain K may have a minimum to maximum. This K is determined, or rather in a polar plot, it is defined using what is known as a gain margin, which is basically the reciprocal of the magnitude of G of the GH of J omega at a frequency for which the phase angle is equal to 180 degrees. Now, look at this drawing. Yes, this one. We are interested in negative 1 plus J0. So this is our Nyquist diagram. So there's a gain. Once you increase the gain, it might reach a point in which it might encycle or not encycle the negative 1 plus J0. So as you increase the gain, this locus might shift towards that point. So at this point is the verge of stability. Either you are increasing from this side or you are decreasing. So at the gain at this point, this is negative 1. It's at the verge of stability. So it is defined, gain margin is defined with respect to this point. Which is defined, there are 4 definitions here. Gain margin is a reciprocal of the magnitude of the gain at the frequency at which the phase angle is equal to 180 degrees. If I draw like that, this 180 degrees. So the gain margin is a reciprocal of this gain. Gain margin is a reciprocal of this gain. At this point, what was the gain at this point? So the gain margin is a reciprocal of this gain. Phase margin is the amount of additional phase lag at the gain crossover frequency required to bring the system to the verge of stability. What is gain crossover frequency? Negative 1. This is your Nyquist plot. Unity. Radius. So, gain, we should have discussed gain crossover frequency. Gain crossover frequency is the frequency at which the gain is equal to 0. The gain is equal to unity. So omega, the frequency at which the gain is equal to unity. This is the gain crossover frequency. And the phase crossover frequency, there is also the phase crossover frequency. This is the frequency at which the phase angle is equal to -180. So this is the phase crossover frequency, of which the phase angle is -180. Yes. So in the design using frequency response methods, we talk about guess, gain margin, and phase margins. I've mentioned about gain margin. There's phase margin. Phase margin is the amount of frequency at which it's the amount of phase lag, It's the amount of phase lag at the gain crossover frequency required to bring the system to the verge of stability. So this is gain crossover frequency. If you are to shift this point to cross, if this curve was to shift to cross that way, if you are to add some phase angle, so this curve, which is coming down, will now go like that direction, so it becomes unstable. So this is the amount of the phase that you are to add. If you are to add some phase so that this curve is rotated in that direction, this curve is rotated now to that direction, to this point of verge of instability, is referred to as gain crossover margin. It's referred to as phase margin, Now, finally, I will just want to say that all this, you can obtain all this information, the phase margin and the gain margin, the phase crossover frequency and the gain crossover frequency. This is body plot. And this is Nichols plot. This is Nichols. This is not really Nichols. Nichols, we have to do some transformation, but it is similar, almost very similar. This is phase log magnitude. Versus phase. So in summary, we have same information. Info, different presentation. You have seen this is phase, gain in rectangular coordinates. This is phase and gain in polar coordinates. But this is phase versus frequency, gain versus frequency in semi-log coordinates. And you can obtain all the same information from each of these curves. So number 2, we plot polar plots. Plot polar plots. Plots. Number 3, Nyquist's criteria. To determine stability. This brings us to the end of frequency response methods. We have only handled one, but the rest have just, it's easy because it's just different presentation, but the same data. So to be able to do that, the first thing is that you have to do omega, G of J omega, and angle of G of J omega. And put random. Values from 0 to infinity. Space here very close. Between 0 to 5, you can put like 5. Between 0 to 5, you can put 0, 0.01, 0.2, 0.5, and 1. And then 5. You can choose 100, 10 power 6, infinity. 1, 2, 3, 4, 5, 6, 7, 8, 9. Around 10 values. Between 8 and 10, and then have this table. Fill this table. And then you'll have, let me check if I have Nyquist plots graph. These are whole exams. Let's check. Let me see if there's a graph. There's no graph. Okay, I'll get the graph, and I'll send you through your class rep one question together with the graph for you to be able to determine the stability of given GH. Use Nyquist to determine stability. Stability. Now, this brings to the end to the section in control. In our syllabus, we are required to have controller design. I have not populated these notes. I have not populated the notes on controller design. We shall revisit this at a later date as I keep on populating. So we will, next time now, we will meet and start discussing instruments. Number 2, we should now be ready for a CAT, a sit-in CAT. I'm going to ask the class rep of this group and the one for the day class. We agree on when we have a sit-in CAT for this, for control systems. And then we move to instrumentations. Instrumentation is more of reading notes. There is no much analysis. But basically, controls is more of design. and analysis. Instrumentation is more of application. Now, up to that point, if anybody feels that there is an area which you would want me to discuss or to revisit, you let me know. I'll spare time, we can revisit. Any question for today? Are we comfortable with the Nyquist plots? Polar plots? We should be. Just do some practice. I will send you a question. You try to plot the polar plot. Hopefully, I'll also see whether I can get a graph for a polar plot and then send you. Are we okay? Are we together? Any reaction? Okay, when I get reaction, it means that. So next time we are now going to discuss about instrumentation systems as I populate the notes on